Model to detect readability improvements in incremental changes. So let's get started by talking about source code readability. So readability is a very fundamental aspect of software quality. It impacts program comprehension, and therefore it affects all parts of the software development process where you're interacting with source code. Readability is also one of the most requested metrics by software developers, yet it's very hard to quantify because it's highly subjective. So you could get 5 developers in a room and ask them to rate a piece of source code by its readability, and you would get 5 different answers. It's a very difficult problem trying to quantify the readability of a piece of source code. However, that hasn't discouraged us researchers, and several models have been proposed over the years that are able to quantify readability. So in 2018, Petricina et al. Performed an empirical investigation into how developers' perception of software quality, including readability, aligns with source code quality metrics that have been proposed. And so what they did was very interesting. They looked at commits where developers had explicitly stated that they were trying to improve a certain software quality metric. And then they measured quality metrics on the pieces of source code before and after the commit was applied to see how they changed. And they found that developers' perception of quality was not often aligned with source code metrics. Now, we were inspired by that study, and we performed our own empirical investigation on GitHub, where we specifically looked at readability. And our study setup was very similar to that of Petricina et al., where we looked at commits where developers had explicitly stated that they were trying to improve the readability of the source code. And our findings were very similar to what Petricina et al. Had found. Developers' perception of readability was not aligned with the readability scores that were assigned by state-of-the-art readability models. It was quite interesting, as these state-of-the-art readability models had been evaluated at the time that they were proposed, but they were never evaluated on incremental changes. So you might ask, why are incremental changes even important? Well, most of the everyday work performed by developers involves incremental changes. Now, if we are able to detect readability changes in the context of incremental changes to source code, now that would allow us to develop better tools to support software developers in their everyday work. So an obvious application of a tool such as this would be to integrate that into the code review process, and reviewers could then use that information about what parts of the commit result in an increase versus a decrease in readability to better inform how they partition their reviewing time. So it is clear that we need to develop models that can quantify changes in readability in the context of incremental changes to source code. In this work, what we wanted to do was we wanted to actually tackle this problem and develop a model that is able to quantify readability improvements in incremental changes. That brings us to the first research question that we posed in this paper, and that was, can we use machine learning to capture readability improvements in practice? So let's talk about how we went about developing our model. And obviously, the first place to start is the data set, because when you talk about machine learning models, your model can only be as good as the data that you provided. So we use some of the data that we had earlier used in our 2019 study on readability, and we went ahead and augmented that with 13 new projects. And in the end, we were left with 2,700 commits from 76 engineered Java projects to use for our model building process. Now, these commits consist of either commits that were intended to improve readability by their authors or non-readability commits. So non-readability commits are any commits that did not intend to improve the readability of the source code. And I want to point out that that does not necessarily imply that these non-readability commits degraded the readability of the source code. We validated each of these commits manually to ensure that they didn't contain a lot of noise. So for example, there might be readability commits where the developer also introduces new functionality, and we do not want these commits in our data set because that would introduce too much noise for our model to learn from. So once we have our data set already, we need to create a representation of this data set so that our model can learn from it. And the way we went about doing this was we calculated metrics, and we used these metrics as a proxy to represent our source code. So we collected a wide variety of metrics from 7 tools, and they broadly fall under 4 categories. So first we have traditional source code metrics such as health at effort, cyclomatic complexity, and maintainability index. So basically all the cohesion complexity documentation metrics that you think of when you talk about software quality. Next, we have metrics that capture fine-grained changes to the source code. So basically, we were talking about substatement level changes in the source code. So for example, if you modify the predicate of an if statement, that would be a certain type of fine-grained code change, and we use a tool called Coming that comes with its taxonomy of source code changes, and we capture the changes that occur in each file using that tool. Next, we look at tools that check for conformance to certain programming practices or conformance to certain style guides, and these tools include PMD and CheckStyle. They're pretty widely used in the industry when you talk about Java code bases, and they're able to capture some information that is otherwise missing in software quality metrics. Lastly, we use a tool called RSM. It provides us with detailed metrics on the lines of code changed in a file. It categorizes them according to logical lines of code, effective lines of code, comment lines of code, and total lines of code. We have our data, we have our metrics, and we are ready to start building our model. We follow a pretty standard model building process. Take our data, we split it into a train and a test set, and we put the test set aside, and we are only going to bring it back out further into the process where we perform our final evaluation. Now we're only looking at the training set, and we perform 10-fold cross-validation on it. And during the 10-fold cross-validation, we're trying to find out the best feature selection algorithm, the best model, and the best hyperparameters for that model. Once this process is complete, we end up with a best configuration consists of those 3 aspects of the model. And we train that on the entire training set. And then we evaluate it on the held out test set that we had earlier. So what does the end result of this process look like? Well, let's look at the results of our first research question. We find some very promising results here. Our model is able to classify readability improvements and incremental changes with a precision of 79% and a recall of 67%. Our results here show that using machine learning in combination with source code metrics is a viable methodology to developing models to detect readability improvements in incremental changes. We qualitatively analyzed the predictions made by our model to identify potential areas of improvement, and we found a couple different patterns in there. We observed that a lot of incorrect predictions were made on changes that affected only a single line of code. This would result in little to no change of the source code metrics that were provided as inputs to our model, and as a result, the model would have a hard time differentiating between readability improving and non-readability commits. So here we have an example of such a change. So here we can see that a class member attribute was changed. So call log options new was changed to call log options, and this was the only change that occurred in the file. And this was supposed to be a readability improving change, but our model was not able to classify it as such. And that was because the metrics, all of the metrics that we collected hardly changed for this commit. The next thing that we noticed was that many non-readability changes included secondary readability improvements. So for example, in one instance, a feature addition required the refactoring of a method that in turn resulted in a secondary improvement in readability. However, the primary purpose of this commit was to introduce the feature, and therefore we did not consider this to be a readability improving commit. So the next thing we wanted to look at was what features were important for our model in classifying commits as either readability improving changes or non-readability changes. So to answer this research question, we used a game theoretic approach to explain machine learning models, which is known as Shapley additive explanations, or SHAP. So SHAP is an approach that measures the contribution of each feature to the predictions made by a machine learning model. So SHAP not only gives you the importance of each feature for a model's predictions, but it also tells you the magnitude and the direction of the influence of that feature. And it does that for every single prediction that you have in your test or training set. So that can give you some incredible insights into why your model makes certain predictions. So we made two interesting observations when we looked at the SHAP values for the predictions made by our model. And the first one was that readability improving commits tend to make changes to existing lines of code rather than introducing new code. On the other hand, non-readability commits, they tend to leave the existing lines of code relatively untouched, and they tend to introduce a lot of new code. And we also found that this new code often comes with a degradation of several software quality metrics, including Halstead effort, Halstead number of delivered bugs, McCabe cyclomatic complexity, etc. So now let's take a look at how our model performs when we compare it with existing state-of-the-art readability models. Let's briefly talk about the models that we consider in this paper. So we considered three models in this paper that we also considered in our previous work from 2019. And these include, firstly, Scalabrino's model, which uses metrics that measure the quality of source code lexicon as a proxy for readability. Next, we look at Dorn's model, which uses visual, spatial, alignment, and linguistic aspects of the source code to measure readability. Lastly, we look at the combined model, which was also proposed by Scalabrino, and it's a combination of multiple state-of-the-art readability models that considers both linguistic and structural aspects of the source code. So if we look at the performance of the state-of-the-art readability models here, we can see that our model is able to outperform the state-of-the-art models in all metrics. For precision and recall, our model offers a performance improvement of 15 and 20% respectively when compared to the best state-of-the-art readability models in those metrics. So once again, we qualitatively looked at some examples in our test set to identify why our proposed model was better than the state-of-the-art readability models. And so the first thing that we noticed was that state-of-the-art readability models struggled with readability improvements that were only comprised of changes to comments. So if a readability improvement only modified comments, state-of-the-art readability models were not able to detect that as an improvement or even a change in readability. If you think about the metrics that we have used for our model, a lot of them actually consider the comments in the source code and how the comments are being changed. So that's one area where our model has a clear advantage over state-of-the-art readability models. Another area where state-of-the-art readability models struggle is that they do not check for any style violations or programming convention violations, unlike our proposed model, which uses data from both checkstyle and PMD. So to summarize, we developed a model that is able to correctly classify readability improvements in the context of incremental changes with a precision of 79% and a recall of 67%. We also showed that readability improving commits are characterized by changes to existing lines of code rather than addition of new lines of code. And lastly, our model outperforms existing state-of-the-art approaches at detecting readability improvements in practice. So that's going to be it for our presentation of our paper, A Model to Detect Readability Improvements in Incremental Changes. And I hope you are able to attend the ICPC live session, and I look forward to discussing this paper with you.